In one of our virtual conferences via Hangouts Meet, I showed how regression line can be used to determine the forecast or predicted grade, and the best fit grade, of course. And how is this related to the practical exams and alternative to practical papers in Cambridge's O level paper 3 and 4, IGCSE papers 5 and 6, and A level sciences papers 3 and 5? Some friends, after told them about that, asked for more in-depth discussion of how Excel can be used for practical examinations or simple laboratory experiments, basically in relation to the papers I mentioned. Other curricula, I am sure, test competencies related to laboratory skills as well. So if you are a science teacher or a student or somebody interested in science who is looking for some possibilities or applications of the idea of regression line and the use of Excel, this video is for you. The video is on how to do judgment and utilize technology, which our students are likely have now in their home due to the distance learning or online learning or home learning, whatever they call it. We will do sample data analysis using Microsoft Excel, specifically with the use of its built-in scatter graph. This is a familiar X and Y plane to teachers and students alike, an XY scattergram. Okay, imagine that a student studies electrical quantities. The setup has this diagram here, and the objective is to determine the effect of voltage to the current. With a voltmeter here, we can read the voltage. This one here is an ammeter for the student to read the current that would flow through this. In online learning, they can do this with some actual materials if available at home or they could get from the outside. If not, perhaps a simulation like this one in PHAT can be used. Now let's assemble the circuit. Okay, this one. Okay, let's go back to the diagram. Check if we did it properly. Okay, now we are ready. Turning the switch on makes the circuit works. And let's imagine the student manipulates the battery, like perhaps putting more dry cells or use a voltage source where voltage values can be altered. Say the student got the data. These are the voltage readings with the corresponding current reading here. By ocular inspection of the set of values in this data table, we can see that the current increases as the voltage increases. In a way, this is already some kind of relationship. Somehow the student is already able to see the effect of voltage to the current. But he decided, for example, to bring this to another level and see if a graph can give him more ideas about his experiment. This set of data is here in this plane. This set here. And quickly we plot all the other pairs of data. Usually people would just try to connect all points. However, in practical exam or any other laboratory experiments, we are dealing with mostly estimates of certain values of quantities. There are likely more minor errors due to limitations of our devices or even errors because of the one who did the experiment. They call it human error. Other things like at the moment we don't have any control, or you may call it extraneous variables. Because of this, we will try to find a line. In some cases, it would be a smooth curve that best fits our sets of points. This is called best fit line. A best fit line, this one, in this case, could be a line that is as close as possible to all points, around same number of points above and below it. This is about, what is that line that is expected in the graph when there was no error. I'll tell you more about this later. Meantime, we proceed on how to do this using the Microsoft Excel. Okay, I'll open Microsoft Excel here. Type in the column title. By the way, the Cambridge recommends some kind of convention where column titles are written in this form: name of quantity slash the unit, like this voltage slash volts and current slash ampere. Itself has a convention. It automatically looks at the left vertical set of data as the manipulated variable, and the other one is the responding variable. These are the same values we had previously. There you go. How now we are ready to insert a graph. You highlight the sets of data first, then click insert. There you go. There you have many types of graphs, but what we need for most data analysis in the lab is this one, is scattergram, or the XY scatter, or simply the XY plane in any mathematics class. Alright, we pick this, and there we have our data plotted in the plane. Next thing is the best fit line. Choose any point in the plane and click it to show this. The one we need here is the add trend line. Trend line, by the way, guys, is Excel's word for best fit line or regression line. I'll save that graph so I can use it in my other app. Okay, here's the graph we had before and the graph I saved from MS Excel. Okay, let's try to compare these two graphs. Points have some distance away from the best fit line, see. We have deviations, which is something worth analyzing as this can give us ideas about experimental errors, human errors, indicates that our device in the lab have some limitations and some factors that we may have no control, some extraneous variables. This is to say that the best fit line in our graph is the line we expect if there were no errors or tools are perfect and that all other variables other than the ones being investigated are well controlled. The best fit line in this case tells us the relationship between the quantities studied in the experiment. In symbols, it is written like this, which is read as current is directly proportional to voltage. If we want to quantify this, or perhaps instead of proportionality sign, we want to use equal sign, then it can be written as this. The K in this proportionality constant and may be linked to the reciprocal of resistance and the Ohm's law. A student can discuss more from there in their report after the experiment. Okay, let's go back to Excel and do other examples. Here's a simple distance time investigation. Let's do the column titles properly. Let's assume some values here and also here. The manipulated variable, or in other schools they call it independent variables, is at the left and the responding or dependent variable at the right of that independent variable. Okay, here. Okay, now we highlight the sets of data, click insert and choose scatter graph. There you go. Let's add the trend line now, or the best fit line. Okay. We can see here that it has the same trend as in our first example. Distance here is directly proportional to the time. If we want to use equal sign, we have this d is equal to kt. The k here is the proportionality constant or the gradient of the line. And student can do discussion of that leading to the idea of maybe the average speed as the gradient. Another discussion students can do is to look at the deviation of points from the best fit line. Evaluation in the premises of errors, extraneous variables, and limitation of tools used can surely be done from here. Alright, let's do another example. Let's go back to Excel, have some pairs of data, highlight this pair of data sets, insert graph, there you go. Let's try drawing the line of best fit. Add trend line by selecting the point. But hey, this doesn't look like a best fit line, don't you think? What we can do in this case is to pick other possible graph that can best fit our data. Let's try this polynomial here. Okay. There we have a parabolic curve. The curve best fits our data. However, we may not be able to write an accurate relation from here. What we will do next is to do some other manipulations. Let me make this smaller first. I'll copy these, retain the values for one variable, and manipulate the other one. Here, instead of just time, we will do square of time in square seconds. We're going to do the same process: highlight, insert, then scatter graph. Now here we have something that likely be best fitted by a line. Let us add trend line. There you go. Hold on, let me rearrange these two graphs here and take a snapshot. Okay. They are showing us two different graphical representation of the values. In this graph at the left, D with unit M is plotted, and here is time with unit second. In the other, D is also plotted in the same manner, but we use square of time with unit square second along the x-axis. Then we follow the same idea as in the previous two examples. If there is a best fit line that looks coming from the origin, it can give a direct proportionality relationship. D is proportional or directly proportional to the square of time. With the equal sign, this notation can be rewritten as D is equal to K square of time. There. Obviously, the proportionality constant K equals D over the square of time. If your students are already aware at this point about some kinematic equations in physics, he can do further discussion of result to claim that decay or gradient gives half of the acceleration of the object. Okay, for the last example, consider a quantity. Let's name quantity y with unit small letter y and quantity x with small letter x as its unit. Just to make it very general. Anyway, in the lab, students experiment on hundreds of variables. We can see the idea that whenever y decreases, there's a corresponding increase in the x. Now, we want to go to another level by doing some graph. Now, same thing. Highlight these, insert scatter graph. There you go. Let's see and add trend line. This doesn't look a good fit. In that case, we can always find other possibilities. We can pick from this right pane in this window. Let's try this. Kind of graph here. There, it looks like a hyperbolic curve fits our set of points. However, we wouldn't be able to use the idea we had with the line in the previous examples. So we can just do some further manipulations. Let me make this smaller. I'll copy these, but instead of x, I want the reciprocal of x in the graph. So let me change this. Okay, there. Same method, highlight, insert, scatter graph. Now you see we have something where a line can be best fitted. Let's add a trend line here. All right, let me rearrange these. Snapshot. Let me fit that on my screen. Hold on. In this case, we have another two graphs that tell the same motion. This hyperbola in y versus x graph and this rising line in y versus reciprocal of x graph mean the same relationship. However, with a straight line here, we can easily use the idea of direct proportionality, that an increase in y would mean corresponding increase in the reciprocal of x. Y equals k over x, leading to the idea that k, whatever interpretation we have, is equal to the product of two quantities x and y. Y is directly proportional to the reciprocal of x, or alternatively, y is inversely proportional to x. Okay, so the change from a hyperbolic curve into a straight line happened when the x is manipulated and changed into this. In the future, after trying the examples above, and still you couldn't make a practically best fit line, you can try a few more manipulations of the values until you end up with a straight best fit line which you can use in generalizing the relationships. Okay, that's all for me for now. I'll try to create a few more to help teachers and students alike or other people who may have interest on topics in the future. All right, thank you for watching.